Hello and welcome to this short video about one of my recent projects, which was a gas level monitor. I needed to understand how much gas I had left in the cylinders at my static caravan, and what I wanted was something that was quick and easy to use. A visual representation showing how much gas was left, maybe a few other items on there, but basically something I could look at quickly and then decide whether I needed to order a new bottle or not. So I started to look around on the internet to see what was available. Some of the devices I came up with, I've broken them down into three price ranges. So the really cheap ones, which were the stick-on magnetic labels, which work on a temperature difference, they aren't much good to me because they're only about 10 centimeters tall, and my 47 kilogram cylinders are about 4 foot tall. So looking at the middle option, which is like an ultrasonic wand, and with this you can run the wand up and down the side of the gas bottle and the tone will change, indicating the level. That's okay, but again it's something I had to do manually and it's not really what I wanted. Looking at the top end of the price range, this looks more like what I needed. So it looks like a platform that the gas bottle sits on, and then that communicates with an app on your mobile phone, and it will show you the weight remaining, percentage used, etc, etc. Now at £130 each, that's quite expensive, so I would need two of those, so that's about £260. I wanted something which was much cheaper and that I could configure myself. The project I designed uses the following parts. So we start off with a 5x7 centimeter project board, standard through-hole plated project board, a few pence from AliExpress. Then we needed a microcontroller, and the one I'm using at the moment, and I quite like, is the Wemos D1 Mini. This is quite a resilient little microcontroller, easily programmed using the Arduino IDE, low current drain, seems to last for a long time and gives very few problems. So when you purchase one of these, you very often get some female DuPont headers with it, and we need a couple of those to mount the TFT screen. The TFT screen I've chosen is the 1.8 inch TFT screen with an SPI interface. Quite just a cheap screen to use. Then we're going to need a HX711 sensor module board, and to go with this we need four 50 kilogram load cells. So the 450 kilogram load cells need to be mounted on something. So for this project for today I'm going to be using a piece of offcut MDF, and we mount the load cells on the MDF using some 3D printed brackets. I just searched Thingiverse for load cell brackets and I found some, printed them off, and they seem to work quite well. So to run this power-wise, normally it's going to be connected to the leisure battery, so we'll need something like an LM7805 voltage regulator. To go with this voltage regulator, we'll need a couple of capacitors. 0.1 microfarad capacitors will do, so we need a couple of those. And then we'll need a couple of JST sockets to connect things like the 12 volt input and the 4 wires that go to the scales. So all of this needs housing in a box somewhere, so I 3D printed a box, and a link to this file will be in the description below. For the wiring, we're going to start with the TFT first. So the first wire we put in is the LED, which goes to 3.3 volts. Then we put in the SCK, which goes to D5. Then we put in SDA, which goes to D7. Then A0, which goes to D4. Reset goes to D0, CS goes to D8, ground goes to the ground pin, and VCC goes to 3.3 volts. The next thing we're going to wire in is the HX711. So looking at that one, we have ground goes to ground, we have VCC which goes to 3.3 volts, we have the DT line which goes to D3, and we have the SCK which goes to RX. Following that, we look at the scales connections. So on the scales we have E minus, which goes to E minus of the 711. We have A plus, which goes to the A plus of the 711 board. We then have E plus, which goes to the E plus on the 711 board, and finally the A minus, which goes to the A minus of the 711 board. Only thing outstanding now is the 12 volt supply. So as you can see on the 12 volt supply, incoming 12 volt plus and minus goes to the 2-pin JST connector, which then goes to the LM7805, a couple of capacitors between pins 1 and 2 and 2 and 3, and then the output, which is 5 volts, goes to the 5 volt pin and the ground pin of the D1 Mini. Here's the component layout and the jumper schedule. You don't have to use this, but it should give you a rough idea of how it should be connected. So here we are, we've loaded the script into the Arduino IDE, and the first thing we're going to do is include some libraries. So the first 3 libraries here are for the TFT display. The next library is the HX711 library for the load cell board. Then we need the EEPROM library because we're going to be storing some of the values in the EEPROM on the D1 Mini. We then have a couple of libraries here which allow us to create the web page and act as a web server. We then initialize the server on port 80, and we do the same, we initialize the HX711 for the scales. Next thing we do is define the pins that we're going to be using for the TFT display. And then likewise we define the pins we're going to be using for the HX711 board, and also we're going to be defining the calibration factor. So it's set to 0 here, but I find that a good value for me was 21145. That gave me quite an accurate result, but we can change that later when we do the configuration via the web page. The next thing we'll do is define some variables that we're going to be using in the web page. Then we're going to define some graphics arrays. Now, graphics arrays here are used to draw the cylinder display and a few other things, the fill level, etc. And if you're not certain how to do this, what we do is we define an array for a particular item, in this case the cylinder, and then that LCIL there is referenced in the tab at the top of the screen called graphics.c, and you can see that it's referenced there. And we can see that it's 32 pixels wide and 112 pixels high, and then this is the code that actually creates the bitmap. And that code is generated easily enough. There are videos out there on YouTube that show you how to do that, but what we'll do is we'll do it here today. So there's my picture of the cylinder done in MS Paint. If you look at the size of it, it's 32 by 112. So once I've defined and drawn my picture in black and white, it doesn't matter, then I'll save that file. Once I've saved it, I'll go to a website, and this is the website I tend to use. It seems to be quite good and does me okay. We load the image, so choose the file, choose our cylinder, open, then go right to the bottom, and then there's an option there, a little preview, there's an option to generate the code. Click on there, it generates all the code for us, and we take everything from those 2 comments to that curly bracket there, including the semicolon. We copy that and we paste it within this graphics.c document. Now the only thing we need to change is the name. So you can see here we've got constant unsigned LCIL, but actually in the web page it's called constant unsigned EPD bitmap cylinder. So I've just named mine LCIL to save typing really. So I just rename it there, and that LCIL there is actually referenced in the code itself there. Okay, so you do the same with the fill and the same with the logo. Then we're going to be declaring some variables for the update rate. That's again changed on the web page. We have a load of colours there, so should you want to change the colours of the display, there's a lot to choose from, and you can delete the ones you don't really need. I've left them in there just for you to use. General variables, we just put those there, and then we define the top and the bottom of the cylinder as pixel values. So that's the length of travel for an empty to full bottle. In the setup process, we start the serial monitor just in case we need it. We start the Wi-Fi as an access point, so that means it's going to sort of display its own SSID, and we create the SSID with this command, Wi-Fi soft AP, and we're going to be calling it silmon space, and then we're adding to that the last 5 characters of the MAC address of the D1 Mini, and that means that each D1 Mini that you use will be unique, so you can have multiples of these all in the same place. Then we define the password, and again I've chosen Silmon plus the last 2 characters of the MAC address. So for example, it would be something like Silmon A9. Then what we're doing is initializing the TFT, and we rotate the display 90 degrees clockwise into landscape mode. We then draw the bitmap for the boot logo, and then we initialize and 0 the scale. Then we start the EEPROM, and we then get to check if this is the first run. If it is the first run, then the EEPROM is going to be full of random variables. So we check if the first run, then what we're going to do is load some sample values in there based on my installation, basically. Then we'll reread the EEPROM just to make sure it's gone in there, or if it wasn't the first run, it'll read what was in there before. We start the server, and then we'll go to the main screen to show the main details. Okay. The loop procedure doesn't really have much in. We just talk to the server and we show data. That's it. Then here, the TFT gas level display, this is the bit that actually draws the level. So we're setting up a for next loop based on an integer called I, and this goes from the bottom of the cylinder to the top of the cylinder, so it's going bottom upwards, and the increments it goes to in is sill size divided by 80, 80 being the number of pixels between low and high. Once we've got that loop set up, we then do a check, and we say if I is greater than or equal to the gas level, then draw the bitmap called fill, which is just a line really, in green. If it's not, then draw the same bitmap in black. And what this has the effect of is, as more gas is in there, it will make the green part bigger, and as it reduces, the black will overwrite the top part of the green. Then we're going to draw the Tft Graphics. This routine is a bit that's called when we're actually sending the data from the graphics.c. Here's the show main screen. It just prepares the screen and prints all the text on the screen, and then we call the update values routine. Show data is the bit that's actually going to be called every time we refresh. So this is where we decide if it's been refreshed or not, and if so, we're going to call the update and populate all the variables. Then when we come to display these variables, there's one line here which is of interest. It's the next line down, which is the TFT fill rect, this one here. And what this one does is, if you try and clear the screen of a TFT, then the whole screen will flash. And all this does is it creates a black square over top of the variables that are going to change. And then as you clear them, you reprint the variables immediately. So the net effect is you don't really see the flicker. It seems to work quite well. There's all the variables, of course, that we're going to be updating with the level, the weight, etc., etc. Here's how we read the EEPROM. So we're just getting the tail level, the cylinder size, the calibration, etc. This is how we write the EEPROM. We only write the EEPROM if the value has changed. So if on the web page we don't update a value, we don't write it. If it does change, then we write it, and then we put those on the EEPROM again. And then the web page stuff, I claim no responsibility for this. I don't know how to write web pages. I effectively borrowed this from another YouTuber and worked out how some of it worked, changed it for what I wanted, and then published it here, basically. Once we've done all of this, the next thing we can do is we can hit the upload button, and we can upload the code into the D1 Mini. Let's start the build. So the first thing I've done, printed out the layout onto a piece of paper, and I've got all the components in front of me now, as we've seen before in the previous slides. So start with the project board. You can see here what I've done is on this side I've actually marked where all my sockets go, just so it makes it easier, that's all. Okay, so the first thing we're going to do is we're going to fit the D1 Mini. Notice the Wi-Fi antenna is facing downwards. So in we go, that goes into there. The edge of this lines up with the edge of here, and it still allows us to plug in the micro USB for charging and for programming. That's the first one in. Then the next one is the HX711. notice the ground, DT, SCK and SC and VCC are at the top, and they go in there. Okay, done. We can now add in the 7805, and that goes here, like so. 2 capacitors, so here and here. If I can pick them up, there we go. Not the easiest of things to pick up. There we go, 2 capacitors. And then we want the female connectors for the TFT screen. So the 4-way one goes here, and the 8-way on the other side. There we go. So that's the first fit. So you can see here the orientation of the D1, antenna at the bottom, 3x3 at the top, and so on. So the next thing we're going to do is turn this over, and we will solder these components in place, and then I'll be right back. Okay, so the parts are now soldered into place. You can see on the back I've trimmed off the legs. I've only soldered the D1 Mini pins that are actually in use. So the ones that are not connected I've left free, just in case I need to remove it at any time. You can see I've also soldered the 2-pin JST and the 4-pin JST. So if you turn that over and look at the jumper schedule here, you can see as it should be 3rd row up, 2nd pin in, which is the 2-pin, and so on for the 4-pin. Okay, so now that we've soldered all those parts on, we can test the fitting of the TFT. So take the TFT, 8 pins, 4 pins, locate in there, locate in that one, and there we go. We have, that's now fitted exactly as it should be. If we take the case, the 3D printed case, the lid, you can see that on one side of the lid there's more space than the other. That's to account for the offset of the screen. So the more space goes this side, fit that on the top. There we go. There we go. So that's what it looks like when it's done. And if we turn the board over, you'll see that the project board fits neatly inside, flush with the bottom of here. A couple of pins in here, a couple of screws in here to hold that safe, and that is now complete. So we can now move on to the actual jumpering. And as it says on the schedule here, that the jumpering is on the reverse side of the board. So all the jumpers will be on this side. When it comes to doing the JST, we may have to run some on this side, but we can remove that to give us a bit more space. Okay, so that's the next stage, is to do all the jumpering on this project board. Okay, the jumpering is now completed. As you can see, I've used the top of the board for the HX711 bottom connections. Also quite finicky, but you can see that there is the 12-volt jumpers there. On the reverse side of the board, you can see all of the rat's nest of jumpers. Now the only slight change I've made personally is to put a 100 ohm resistor in series with the LED backlight, just so it dims it down just slightly. If I had my time again, I'd probably design a PCB for this, which would get rid of all this rat's nest and make the layout much better. But as you can see, that's the finished item. So all that remains now is to plug in the TFT display. So as we saw before, done. Okay, and then the next thing is to upload the code. So from here, here's the micro USB, in it goes. So you can see all it does at the moment is just bring on the backlight of the TFT. If I now set the compile and upload the code, that will take a few seconds really. Okay, it's almost done. And there we go. So you can see the display is there. Obviously there's no scale attached to it yet, so it's not going to show an awful lot, but you can see the refresh time, etc. And that's the finished item. So now that we've got the code uploaded, what we can do is we can put this into the case itself. Okay, that's the next stage. So unplug, we'll take the lid of our case again, noting the extra space as we said before. Extra space goes here, in it goes. We take a couple of screws, okay, one in there. 2 screws is usually enough, that's fine. Okay, done. Now we just need 12-volt power and then the scales. So at the moment we just have 12-volt power. So here's 12-volt power on a 2-pin JST. So we insert that in there, and as you can see, it powers up again. So we're now running off 12-volt power. Okay. So ideally, we take that off, take the case, plug in, turn it around. There we go. And then we just basically put a couple of pins in there to hold the lid on. And that's the finish. For the scales, I printed out the diagram, which is on one of the slides. You can see here, so you have upper left, upper right, and then lower left here, which is just off camera, and lower right down here off camera. And you can see it says view from underneath the scale. So as we look at my scales here, this is how we're going to be wiring up. So just to make things easier, I've included a little piece of Vero strip here, which is where I've done all my terminations. But you can run the cables any way you want, and you can twist the ends together, solder them, heat shrink them, etc. So starting with what we have on the board, I'll try and bring this up so you can see. So you see that you got the upper left. This is the 3D printed bracket. Here's the load cell. You can see that this load cell has 3 wires, red, white and black. Sorry, red, white and black. Same with this one for the upper right. Same with this one down here, which I can't show you, for the lower left and the lower right here. So we've got a total of 12 wires to play with. So using the diagram that's in the slide, you can see that starting with the upper left, the black cable of the upper left here is connected directly to the black cable of the lower left, which is down here. The white cable of the upper left is connected directly to the white cable of the upper right, and the black cable of the upper right is connected to the black cable of the lower right. So the whites and the blacks are fairly straightforward. For the red cables, each one has its own designated letter, E minus, A plus, etc., etc. And that corresponds with the silk screen printing on the HX711. So the upper left, red, goes to E minus of the HX711. The upper right, red, goes to the A minus of the HX711. The lower left, red, goes to the A plus of the HX711. And finally, the lower right has the red wire connected to the E plus of the HX711. So you can see that I've used a piece of board, which this is about 40 centimeters wide here. Say a little bit of Vero board just to do my connections. If this was going to go outside, say for a static caravan or something, then obviously MDF is no good. You'd have to use something like aluminium plate, and I'll show you a couple of photos shortly of the setup that I've actually got. I've actually got 2 scales because I've got 2 bottles, and they're side by side. So I went a bit overkill with mine. It would support our house, I think, but it was just my prototype. So I'll show you what mine looked like, and maybe you can take inspiration from that. So once we've done the connections down here in the middle, I've run off the 4 wires that would go to the HX711 and terminated those on a 4-way JST, and that would go into the JST connector on the back of the head unit. Here's an example of how I made my scales. I used 40mm angle iron welded together to form the framework, and then the actual bottles themselves sit on top of 2 sheets of aluminium. Now I have 47 kilogram bottles on the back of my Caravan, and it needs to be weatherproof, which is why I use the aluminium, and the load cells are fastened underneath the aluminium. So I use actually 8 load cells, and I've got 2 of the head units built in my Caravan. When we did the code walkthrough, we said we were setting the D1 Mini as an access point so that it would broadcast its own SSID. SSID being made up from the words Silmon and the last 5 characters of its MAC address. And then the configuration is done via a web page. So switching the head unit on and then using my phone to search for available networks, we should see the SSID being broadcast, and there it is, Silmon 82:B4. If we select that, it gives us then the chance to enter the password, which was configured within the code, and you can set that to whatever you want really. Once we've entered the password, we can hit the join button, and when we hit the join button, it will connect us to the access point on the D1 Mini. It takes a few seconds, and it is quite short range, so you need to be within sort of a couple of meters, 4 or 5 meters maybe, of the head unit. There's a configuration page. So to use this, on the configuration page there are 4 items. The sample rate is at the top, and that's defaults to 5 seconds. It has a range of 1 to 7,200, and it's used for setting up the frequency at which we'll go away and get the weights. Calibration factor, preset in the code again, and it has a value of 1 to 99999. The tare weight and the cylinder size are both in kilograms and have a minimum of 1 and a maximum of 47 kilograms. So we enter the values in there, and when we've done that, we hit the save configuration button. So any values that are in there are sent over to the head unit. Anything that's blank is ignored. So if we take a look at the head unit, we can see we've got a refresh rate of 5 seconds. I'm going to change that to 2. Cylinder tare, the empty weight of the cylinder, I'm going to set to 35, and then the cylinder size, I'm going to set that to 47 kilograms. And when I hit the save configuration, it will reflect those values onto the head unit, and you can see we have a refresh rate of 2 seconds, tare of 35 kilograms, cylinder size of 47 kilograms. When calibrating the unit, we need to have a known weight. Try and use a weight which is as close to the gas bottle weight as you have. So I have a 47 kilogram gas bottle with 35 kilogram tare weight, a total of 82 kilograms. And once I've calibrated here at home, I would then install the unit at its final destination in my Caravan or patio heater, wherever, and then I'll recalibrate. This way it'll take into account any additional resistance caused by any cable runs. So I'm going to use my bathroom scales and weigh myself, and I'm looking like I'm locked out at 88.9, which is fairly close to my 82 kilograms. And then once I've got that value, I can step on the monitor scales, and you can see that it's reading approximately 88.85, so it's a little bit low, and I need to adjust the calibration factor. So when we adjust the factor, the higher number we put in here, the lower the weight will be. So it's opposite. So I'm going to enter here 21155 and see what happens. So enter the number, save configuration. Notice it changes on the head unit, and I'm now reading 88.4883. It's a bit difficult for me to keep still while I'm trying to film. So that's not quite right, so let's change the factor again. And this time we're going to enter, I don't know, 21100. So we're going to go downwards, which should increase the weight on the screen. And sure enough, there we go, 89.04 kilograms. So it's getting close. So let's try once more. And here we just go back and let's enter, I don't know, 211. Let's go 21115, I think. That's probably going to be about right. So we enter that value, we update the values, and there we go, 88.99, 88.9. So we're now configured and ready to take the unit to site. Well, that's the end of the video. I hope you enjoyed it. If you've got any questions or comments, leave them down below. I'll try and answer as many questions as I can. And thanks for watching.